In this lecture, I am going to continue the autocorrelation function properties. In the last lecture, I have discussed the first property. That property is namely the autocorrelation function is bounded by its value at the origin, that is Rxx of 0 is greater than or equal to mod of Rxx of tau. Now I would like to say some more points about this. So as you can see, in general, you could also intuitively see that the magnitude of Rxx of tau cannot be more than the value at tau equal to 0. So this is the autocorrelation function at tau equal to 0. So the autocorrelation function at any value, any arbitrary tau value cannot be greater than the autocorrelation function at tau equal to 0. By definition, we know that Rxx of tau is equal to expected value of multiplication of two random variables x of t1 times x of t2. Again, for the same reason, you can expect the maximum correlation occurs when the two random variables are the same. So this is a correlation. The maximum correlation occurs when x of t1 and x of t1 are the same. The moment you sample at different time instance, like you have a random variable, a random process like this, and let me denote the random process by x of t. You sample the process at time t and some other different time instance at t plus tau, and this difference is going to be tau. Then the moment you sample at different time instance, then they are different random variables. So therefore they can have correlation. The moment you have two random variables, x of t one random variable, x of t plus tau another random variable, so there is a correlation between the two, right? So this correlation will always be less than the correlation with the random variable itself, because you can expect the maximum correlation between the two same random variables. Therefore this Rxx of the autocorrelation function Rx of tau, that is correlation between x of t and x of t plus tau, will always be less than the correlation that you will have of random variable with itself. So you find the correlation with x of t itself, and this will be maximum. Then the correlation between the two random variables which are sampled at a different time instance, because here you can expect a perfect correlation. So if you take the correlation with itself, correlation of a random variable with itself, you will get a perfect correlation. So when I say perfect correlation, then you can expect a maximum value. So that's why in total you can say Rxx of tau, take modulus, and this will be always less than or equal to the maximum value Rxx of 0. And this tau is sometimes called a lag variable. Because a lag between the two time instants t1 and t2. t2. Note: please understand that Rx, the autocorrelation function Rxx of tau, is not a random quantity. Okay, so the autocorrelation function is a highly deterministic function. Because we are basically looking at this like or xx of tau, the autocorrelation function, which is let's say x of t1 times x of t2. I can use any one definition, nothing is wrong in that. I can put x of t and x of t plus tau, or x of t1 times x of t2 and take expectation. So by definition it is double integral, because the joint density function is involved in this integration. So x1 and x2, the joint density function x of t1 times x of t2, the sampled values are x1 comma x2. Put a colon here, or some authors put a semicolon, nothing is wrong here in this notation. t1 comma t2 times dx1 dx2. Okay, now unlike x of t, what is x of t? Your random process. Unlike x of t, which is a random process, right? Random process. Or xx of tau, that is our autocorrelation function, which determines the second order properties of the random process x of t. Or xx of tau, you can write like this, or xx of t comma t, or xx of t1 comma t1, or you can say or xx of t2 comma t2, or deterministic functions which determines the this is t1 and t2, or t1 plus tau, that's it. This is t1 and that is t2. I am repeating. So this determines the second order properties of the random process. In short, I use RP, random process. Therefore, the autocorrelation function tells you the behavior of the random variables with respect to each other on an average. So you have two random variables, let's say x1 or x of t1, and another random variable x of t2. Okay. Now on an average, what is the behavior of the two random variables with each other? Okay. So then you just take the product of these two random variables and take the expectation operation. So how do you get this x of t1 and x of t2? By sampling the random process at different time instants. For example, you have realization like this, and there are many realization like that. Sample the process at t equal to t1, you will get a random variable x of t1, and again sample the process at time instant at t equal to t2, you will get another random variable. First you multiply these two random variables and then take the expectation operation. So multiply these random variables and looking at the average value of this product. And basically this is some kind of characterization of the process basically it is called the second order characterization of the random processes. Therefore the autocorrelation function or xx of tau is a value. You will get some numerical value. So it is a fixed value for a given random process. Is a fixed value for a given random process. It is a fixed value for a given random process even though the random process x of t is random nature. See, the input is x of t and this is a random process. It is a random in nature. But once you do the sampling and get two random variables and multiply those two random variables and take the expectation, finally you will end up with a deterministic quantity, a fixed value for the given random process. So therefore, even though the random process is random, but you will finally achieve, or finally you will get a deterministic quantity. In autocorrelation function, there is nothing random. Okay, therefore Rxx of t comma t or Rxx of tau, there is no randomness in that. Okay, so lots of correlation functions are deterministic functions. This is an important point, please note it down. Lots of correlation functions, deterministic functions. Okay, now let me come to the second property. The second property says the autocorrelation function Rxx of tau is equal to Rxx of minus tau. So that means the autocorrelation function is an even function. Even function with respect to what? Even function of tau, with respect to tau. Therefore, the second property indicates that an autocorrelation function has even symmetry. The proof is very simple. By definition, the autocorrelation function is equal to the expected value of product of two random variables. Let me say x of t times x of t plus tau. Now put tau equal to minus tau, replace tau by minus tau. Therefore, Rxx of minus tau is equal to expected value of x of t times x of t minus 2. Mathematically, let me prove this, and then later on I will give the conceptual understanding of this. Now substitute or let eta is equal to t minus tau. Therefore, t is equal to eta plus tau. So take these two substitutions. From this you will get this one. Therefore, Rxx of minus tau is equal to expected value of t is replaced by eta plus tau times t minus tau is eta, and put like this. Then it's after all it's a multiplication, right? You can interchange or put x of tau first, then x of eta plus tau second, and again instead of t I have this random variable, instead of t here I have this random variable. So what is the difference between this guy and this guy? This is a time index actually, by the way, time index, and this also time index. What is the time difference between these two guys? Eta plus tau minus eta, again tau. So once again this is Rxx of tau. So the proof is like Rxx of minus tau is equal to Rxx of tau, which proves the second property. So this is an important property of an autocorrelation function for a real valued process. Sometimes I simply use the word process when I want to say random processes. Now the third property is Rxx of 0 is equal to expected value of x square of t. This is very simple, very straightforward proof. So first let me write down the definition of autocorrelation function, which is expected value of x of t times x of t plus tau, and substitute tau equal to 0 in this. then Rxx of 0, which is expected value of extremely simple proof, a trivial proof. That's a proper way to say trivial proof. So expected value of x square of t. What is this? This is a mean square value of the process x of t. Value of the process x of t. So it's a very simple, straightforward proof. Okay, so at this point let me stop. In the next lecture I'll continue to discuss the remaining properties. Thank you very much.